Welcome to the workshop. Today we want to take a look at series and an example of determining if a series converges or diverges. So for this example, of course we want to determine if it converges or diverges, and if it does converge, we want to find the sum. The first sum that we're looking at is, or the first series that we're looking at, is the sum from n equals 0 to infinity of 5 over 3 to the n. So a quick reminder that this looks something like 5 divided by 3 to the 0 plus 5 divided by 3 to the first, and so on. Okay? So we want to notice that this is equal to the sum from n equals 0 to infinity of 5 times 1/3 raised to the nth power. Now, why do we want to observe that? Well, because this tells us that it is a geometric sum, or a geometric series. Geometric series with, let's see here, we have an a value. The value out front is 5, and the value, the ratio is 1/3. R is 1/3, or the rate at which it's growing. So in this case, it converges for any R value less than 1, and that's what we have. We have a value less than 1. So the sum converges and we have a nice formula to determine what the sum converges to. Again, that's going to be the A value divided by 1 minus the R value. So 1 minus 1/3. Well, that's just 5 times 3/2, which is equal to 15/2. So the sum converges to 15/2. Excellent. So that's the first example. For the second example, we want to recognize that again, we actually have a geometric series. And in this case, let's see here, we don't have to do any manipulations to observe it as that. Our A value is given right away, as well as our ratio, or our rate of growth. So this is a geometric series with A equal to 1 and R equal to 5/3, which is greater than or equal to 1. Because we have an R value of 5/3 greater than or equal to 1, this series diverges. Alright, so we know the series diverges. Now, for this example, we could also look at it in a different light. We could look at it as, let's see here, limit as n goes to infinity of 5/3 to the n. If we have a series that converges, the terms must go to 0, because in order for us to end up with a finite value, what we're adding on has to be essentially nothing. If we continue adding quantities that are large, then of course our overall value is going to continue growing. So we need this limit to equal 0 if it's going to converge. Now, it equaling 0 doesn't guarantee convergence, but if it's not equal to 0, it will guarantee divergence. So in this case, this limit is infinite or does not exist, depending on what you're talking about here, right? It does not exist as a real number. It is an infinite limit. All right, so by the nth term test, the series diverges. So there are two ways that we can approach this problem. Either observe it as a geometric series with an R value of greater than 1, giving us the conclusion that it diverges, or use the nth term test, observing that the nth term does not go to 0, so the series diverges. Either way, you end up with the same conclusion. And again, in the first case, since we had an R value of less than 1, the series does converge, and we can use A divided by 1 minus R to give us what the sum of the series is. Excellent. So we'll take a look at a few more examples of series here shortly.